It's a little poetic, really. Enrico Fermi, the man who helped unlock the power of the atom, also gave us the question that's haunted astronomers for decades. Where is everybody? Maybe the answer is simple. Life needed radioactive isotopes to begin, and on many worlds they decayed before it happened. We often ask why the universe seems so quiet. Where are all the aliens? Why don't we see any signs of them? No massive interstellar empires, no great beacon shining across the void, not even a stray probe. This mystery is famously called the Fermi paradox, named for physicist Enrico Fermi, who once posed the haunting question, where is everybody? When Fermi made his famous remark, the space race hadn't even started yet, let alone the moon landings. The Cold War, however, was already underway, and it featured the very nuclear weapons he had helped invent. So his default assumption was that space travel was extremely difficult, perhaps even impossible, and that civilizations would be far more likely to destroy themselves than to build and maintain giant transmitters for thousands of years. Interstellar travel seemed unlikely, colonization of dead worlds at the end of such a trip almost absurd, so the only way we would detect alien signals was that they kept broadcasting powerful signals across the stars, and didn't blow themselves up first. This became the de facto answer to what later be called the Fermi paradox, though the term itself would not emerge until the mid-1970s, after the Apollo program. We had both survived the Cold War so far, and sketched out the basics of interstellar spacecraft designs, and some terraforming and space habitat concepts. At that time, the main competing theory wasn't that civilizations inevitably self-destructed, but that life itself, especially intelligent life, was simply rare. These two views form the early foundations of the paradox. Either life is common, but intelligent species tend to destroy themselves, or fail to spread, or intelligent life is incredibly rare to begin with. Since then, many other camps and variations have emerged, but these remain the two classic interpretations that started things off. And yet, while nuclear power is essentially the center point of the first case in its destructive form, could it actually instead be the reason for this second case, that nuclear power spawned life? What if the answer lies not in nuclear destruction, but in fission-powered birth? What if the reason we don't see anyone out there is because life itself is just that rare, because the circumstances for it coming to be are uncommon and short-lived? And what if the key to unlocking that mystery was something Fermi himself helped pioneer? The nuclear reactor. On Earth, the very first self-sustaining nuclear chain reaction did not happen in a laboratory or a test site. It happened naturally. Billions of years ago, uranium-rich rock, water, and time came together to ignite a slow, smoldering atomic fire in the depths of the Earth. And from that strange, ancient chemistry, life may have emerged, not in a tide pool or vent, but a nuclear geyser. In today's episode, we will explore this incredible idea that the origin of life on Earth may have required a very specific, very rare, and now mostly impossible event, a natural nuclear reactor. And this could explain not only why we are here, but why no one else seems to be. The Fermi paradox and the Great Filter. Let's begin with the paradox itself. The Milky Way galaxy alone contains over 100 billion stars. Even if a tiny fraction have habitable planets, there should be millions of worlds capable of supporting life. And if intelligent life evolved on just a few of them, given enough time, it could have spread across the stars. Indeed, even from neighboring galaxies like Andromeda, as there are many stars between that serve as bridgeheads. Civilizations could rise, send out probes, build megastructures, or at least leave behind some sort of cosmic graffiti. But instead, silence. We see no Dyson spheres, no alien signals, no von Neumann probes, just a whole lot of emptiness. This is the Fermi paradox. One popular explanation is the concept of the Great Filter, a hypothetical barrier or bottleneck in the development of intelligent life. Maybe life and the conditions that spawn it are rare, and we would call these early filters. Maybe it's common for life to form, but rare for complexity or intelligence to evolve, and we call these mid-filters. Or maybe civilizations destroy themselves with nuclear weapons or rogue AIs before they can colonize the stars, We call these late filters, as they take place after the here and now, hurdles we must still survive to get to space. And the two default ones are self-destruction and making interstellar colonization practical and desirable. Now, none of these are exclusive. You could have tons of filters, each contributing a little and winnowing us down at each stage, but we tend to assume one single great filter or a few major ones did most of the winnowing. In our timeline context, if that was in the early filter stage, we have a galaxy full of worlds where no life or biology ever emerged. In the mid-filter context, a galaxy full of life but not intelligent life, and perhaps not much above lichen or algae. And in the late filter's case, a galaxy full of graveyards, either entirely dead or built upon layer after layer of cyclic tomb worlds, at best stay-at-home civilizations that have no interest or ability to speak to anyone beyond their own star system. We have many rival scenarios to the Great Filter approach as well, such as perhaps the universe is full of quiet alien empires who deliberately hide themselves, like hunters in a dark forest. A lot of discussion goes in these mid and late filters, or alternatives to permit aliens to be uncommon but unseen by us. But while I take all the filters seriously, I think those early ones, buried in the ancient primordial days, may be the best. That the Great Filter isn't waiting for us in the future, but lies far behind us, at the very beginning of life and before. The Rare Earth Hypothesis and LUCA. To explore that idea, let's take a brief tour through the origin of life theories. Modern biology rests on the principle of common descent. All known life shares remarkably uniform biochemistry, DNA and RNA to store and transmit information. ATP is the universal energy currency, lipid membranes to enclose cells, and a standardized genetic code to translate between nucleotides and proteins. This deep molecular commonality points to a single ancestral organism, LUCA, the last universal common ancestor. But LUCA wasn't the first life form, it was simply the earliest one that managed to leave descendants still alive today. There may have been many other primitive cells before LUCA, organisms that lacked full replication machinery, that failed to adapt, or simply outcompeted. It's possible the first true cell capable of division lived and reproduced many times before one of its offspring stumbled on some evolutionary advantage and went on to found the entire tree of life. That founding event may have occurred one division later, or 20 or 20,000. We'll never know exactly where LUCA sat in the branching chain, only that everything alive traces back to it. And that's the catch. By the time LUCA appeared, life already had a robust toolkit, DNA, enzymes, and genetic translation. That raises a deeper question: how did such complexity arise? One prominent hypothesis is the RNA world model. In this view, RNA predates DNA and proteins. It may have once served double duty as both a genetic blueprint and a biochemical workhorse. Unlike DNA, RNA can fold into intricate shapes and catalyze reactions, acting like a molecular Swiss Army knife. It's a logical candidate for bridging the gap between simple chemistry and full-fledged biology. Other theories emphasize the emergence of metabolism first, or propose that lipids self-assembled into protocells, primitive bubbles of chemistry, perhaps capable of growth or division even without true heredity. There are also hybrid models that combine these pieces, self-organizing membranes housing RNA-driven reactions, with energy gradients feeding the whole system. This falls under the umbrella of systems chemistry. So, where could such chemistry happen? Commonly proposed environments include hydrothermal vents on the ocean floor, tide pools and warm ponds, volcanic springs rich in minerals, clay surfaces that could help catalyze reactions. Each of these provides heat, water, minerals, and the potential for concentrating molecules. We don't know how life started, but we can deduce that if it occurred by random chemistry, then we needed the environment to be favorable to that chemistry. But here's the problem for figuring out which candidate did it. They are not rare. Early Earth had all of those options, and so might countless other planets and non-planets too, like moons. Yet curiously, all known life appears to trace back to a single origin. If environments like tide pools, volcanic springs, or hydrothermal vents are so widespread and persistent across Earth's history, why didn't life start more than once? Why don't we see other lineages with different genetic codes, alternate biochemistries, or non-standard amino acids? Now, it is entirely possible that life did start more than once, but only one version survived. Early Earth was a chaotic and often hostile place, with asteroid impacts, radiation, and wildly shifting climates. Any fragile chemical system would have had to compete fiercely for space and resources. The first lineage to get a head start, particularly one that involved DNA, proteins, and efficient replication machinery, could have easily outcompeted or consumed its rivals. Just like apex predators dominate ecosystems, one biochemistry may have dominated the entire biosphere. This would tend to imply, though, that life was incredibly common in the cosmos. If it evolved here multiple times independently, and thus we would be limited to mid and late filters to explain its apparent absence elsewhere. Alternatively, perhaps life is harder to start than we think. The conditions required might be so narrow and fleeting that they only occurred once in all of Earth's 4.5 billion years, a notion central to the rare Earth hypothesis. This idea argues that while Earth has many life-friendly features, the actual spark of life may have required a perfect storm of rare factors. Not just water and organics, but energy gradients, metal-rich surfaces, perhaps even exotic chemistry, something precise and perishable. Something like a natural nuclear reactor. Natural nuclear reactors, Earth's first fission furnaces. Let's look at how that's possible. Uranium is a radioactive element forged in the hearts of dying stars, specifically during supernova explosions and neutron-star mergers, where the intense conditions are capable of producing the heavy elements. When such a star detonates, it not only blasts uranium and other metals into space, but also triggers shockwaves that help compress nearby gas clouds, potentially jump-starting new star systems, like ours. The Sun likely formed in one of these dense stellar nurseries, surrounded by thousands of other stars, some of which were short-lived giants that went supernova themselves. But early planetary systems were hot, unstable places, rocked by frequent impacts and intense radiation. Planets like Earth were far too molten to support life for many millions of years. Yet Earth cooled surprisingly quickly. Within 100 to 200 million years after its formation, it developed a solid crust and condensing oceans. By around 4.4 billion years ago, liquid water likely existed on the surface, and the conditions for chemistry, and possibly biology, had begun to emerge. And crucially, in this early epoch, uranium looked very different. Today, uranium ore contains only about 0.7% of uranium-235, the isotope needed to sustain a chain reaction. That's far too dilute for fission to happen naturally, but U-235 decays much faster than its heavy cousin, U-238. If you go back far enough in time, say 2 billion years ago or more, the natural uranium on Earth had a U-235 content around 3 to 4%. That's just enough to cross the threshold for spontaneous nuclear fission, if the right materials and conditions were present. In Oklo, what is now Gabon, West Africa, those conditions came together. Roughly 2 billion years ago, underground uranium deposits in Oklo became saturated with groundwater. Water acts as a neutron moderator, slowing down neutrons so they are more likely to cause fission in U-235 atoms they bump into, which then spit out more neutrons at high speed. Rinse and repeat. As water seeped into the uranium-rich rock, it triggered a self-sustaining chain reaction, effectively turning the deposit into a natural nuclear reactor. The water acted as a moderator, slowing down fast neutrons through collisions with its hydrogen atoms, which made them more likely to trigger further fissions. But as those reactions progressed, the water heated up, and hot water, being less dense, is a less effective moderator. With fewer hydrogen atoms per unit volume, neutrons weren't slowed as efficiently, and the reaction would naturally taper off. This created a kind of thermal feedback loop, where the reactor would pulse on and off depending on how hot the surrounding water became. And remarkably, this natural reactor stayed intermittently active for hundreds of thousands of years. This was not just a fluke. The Oklo site in Gabon contains over a dozen distinct reactor zones where natural nuclear fission occurred in ancient rock. These events took place around 2 billion years ago, well after life had already emerged, but there's every reason to believe other natural reactors existed earlier in Earth's history. Back then, uranium-235 was far more abundant, making such reactions more likely, even if evidence is harder for us to find today due to erosion and plate tectonics. These natural reactors were not as powerful or dangerous as modern ones, but they still produced measurable heat, radiation, and chemical transformations in the surrounding geology. It's an extraordinary reminder that nature got there first, long before Enrico Fermi built the Chicago Pile 1 in 1942, but the implications go far beyond geology. Because if natural reactors could persist for thousands of years, generating energy and complex chemistry in stable, mineral-rich environments, they might also have served as crucibles for life. The Nuclear Geyser Hypothesis. So how could a natural reactor, especially one involving geyser-like activity, actually contribute to the origin of life? To start with, a functioning natural reactor produces not only heat, but also ionizing radiation, free electrons, and hydrated electrons, a diverse mix of energy inputs that are ideal for driving prebiotic chemistry. When water interacts with this radiation through a process called radiolysis, it breaks down into a reactive species like hydroxyl radicals, hydrogen gas, H2, and hydrated electrons. These radicals and gases, when mixed with dissolved carbon dioxide, CO2, or methane, CH4, create a rich brew of high-energy molecules and reactive intermediates that can fuel complex chemical synthesis. But energy is not enough on its own. Timing matters too. As the uranium-rich rock heats groundwater to boiling, the resulting steam forces water out of the system and shuts down the chain reaction. Once it cools and water seeps back in, the reactor starts up again. This on-off pulsing acts as a kind of self-regulating biochemical clock, a natural metronome that cycles the environment between high-energy reaction phases and low-energy stabilization periods. This rhythm could have helped prevent the destruction of fragile molecules by giving them time to cool, stabilize, and polymerize between pulses. The physical structure of a geyser or underground cavity also helps by trapping gases like hydrogen, methane, carbon dioxide, and carbon monoxide, formed by radiolysis, and holding them under pressure, promoting thermochemical reactions that otherwise might not proceed. This confinement helps build up reactants, concentrate intermediates, and maintain ideal gradients. The surrounding geology adds another essential piece to the puzzle. The host rock of a natural reactor isn't just inert scaffolding, it's an active chemical participant. Minerals rich in iron, calcium, nickel, sulfur, and phosphorus serve both as catalysts for crucial chemical reactions and as sources of nutrients that would later become foundational to life. For example, iron and nickel are key catalysts in the Fischer-Tropsch process, which can convert simple gases like carbon monoxide and hydrogen into more complex hydrocarbons, longer chains of carbons that are essential building blocks for membranes and energy storage molecules. These same metals may have catalyzed early redox chemistry, helping form primitive metabolic cycles. Calcium, while not always highlighted in origin of life models, plays important roles in stabilizing cell membranes and signaling in modern cells, and may have helped early molecule structures maintain cohesion under thermal stress. Calcium was also the most likely divalent metal needed to catalyze the foremost reaction, an autocatalytic process that transforms formaldehyde into sugars like ribose, a major component of RNA. Sulfur, especially in the form of sulfide minerals, is involved in the Sabatier process, which allows CO2 and H2 to convert into methane, a simple organic fuel. Sulfur is also essential for modern protein structure and metabolic reactions, and may have acted as an early electron donor or acceptor in proto-metabolic systems. Phosphorus is perhaps the most vital of all, forming the backbone of DNA and RNA, the high-energy bonds in ATP, the key structural component of cell membranes. Yet phosphorus is often scarce and chemically locked in rocks. Indeed, we did a Fermi paradox episode some years back simply focused on the phosphorus problem. Fortunately, many uranium-rich mineral environments also contain phosphates, and in a unique case of natural reactors, neutron transmutation may even have converted silicon-30 into phosphorus-31, enriching the local rock in a highly bioavailable form. Notably, these catalytic and nutrient-rich minerals are often co-deposited with uranium. The geological processes that concentrate uranium ores, hydrothermal circulation, sedimentation, and fluid migration, tend to gather trace metals and essential elements in the same vicinity. This makes natural reactor sites uniquely suited to prebiotic chemistry, not just places of energy and reaction, but nutrient-rich crucibles, where the raw ingredient for life were literally embedded in the walls. And while the environment may sound hostile, filled with radiation and heat, it may have been just right. The Geyser-like system is strikingly Goldilocksian, hot enough to drive the reactions that build complex organics, but not so hot that those molecules are immediately destroyed. It's enclosed enough to keep ingredients together, dynamic enough to prevent stagnation, and rich enough in energy and chemistry to do something truly special. In essence, such a system wouldn't just be plausible, it might be one of the best prebiotic laboratories nature could assemble. Not just a warm little pond, but a nuclear-powered pressure cooker, complete with its own chemical kitchen and a built-in clock. Enrico Fermi's famous question, "Where is everybody?" pushed us to consider whether the origin of life itself is the bottleneck. Today we are looking at the front end of the problem, that uranium's radioactive gift was both a creator and a limit on life beginning. But it's more classical in the Fermi paradox is as destroyer, at the end of the road rather than the beginning. The late filter none escape from. But what if people do escape civilization-destroying events and rebuild, only to fall victim to them again, and again, and again? Taken all together, it could mean the reason we don't see our galaxy full of alien civilizations much older than us is because they are around but just never managed to keep civilization together long enough for robust interstellar settlement. We'll explore this notion in our new exclusive episode, The Fermi Paradox: Civilization Extinction Cycles, which is out now on Nebula. Every month I release an episode on our streaming service, Nebula, and over the years we've accumulated over 50 exclusive episodes, extended editions, and more there from myself and many other awesome creators. It's also where every episode of SFIA premieres, days before coming out on YouTube and elsewhere, and without any ads or sponsor reads like this one. Get a lifetime membership, normally $500, for just $300 by using my link, and enjoy all my exclusives and all Nebula originals for life. Go to go.nebula.tv/IsaacArthur and unlock everything forever, or get an annual plan for 40% off, $36 a year. That's 12 months for the price of 7. Scan the QR code or click the link below to start watching now. Implications for alien life. If natural nuclear reactors were central to the origins of life on Earth, it reframes the Fermi paradox in a striking way. Rather than asking why civilizations fail to expand or communicate, we might need to ask a deeper question. Why does life ever begin at all? The nuclear geyser hypothesis implies that abiogenesis, life arising from non-living chemistry, requires not just a warm, wet environment and organic molecules, but a very rare and fleeting set of conditions. An environment with heat, radiation, reducing gases, catalytic minerals, and a way to regulate and cycle these inputs over time. A natural reactor does this elegantly, but it comes with severe constraints. First, it's time limited. Because U-235 decays quickly, the conditions for natural reactors faded early in Earth's history. By about 2 billion years ago, conditions for spontaneous reactors were already rare, and in other words, the same radioactive clock applies. If a planet formed too late, or didn't concentrate uranium quickly enough, it may never have had the chance. Second, it's highly selective. The planet must form in a region of space seeded by heavy element-producing events like supernovae or neutron star mergers. It must have enough mass and geological activity to deposit and retain uranium in a way that allows it to accumulate. It also needs groundwater, porosity, and tectonic stability. Not every rocky planet will check those boxes. We'd also include a scenario where our world might be hit by incoming asteroids, or a dwarf planet that was heavily laden with uranium from a more recent supernova, but the odds don't favor that being very common, so we have a factor that fits well with other early filter scenarios. That's important. This hypothesis is non-exclusive, and thus doesn't have to be a great filter all on its own. It doesn't deny the possibility of later filters. Even if a planet gets lucky and births life from a uranium-fueled geyser, it can still lose that life to environmental collapse, asteroid impacts, or civilization-ending technologies. Indeed, there's a tragic symmetry to the idea that the same element which might give rise to life could later be used to destroy it. But in the context of the Fermi paradox, this view shifts the focus. Perhaps we don't see alien civilizations not because they're hiding or because they've destroyed themselves, but because they never got started. If the conditions for life are as rare and fleeting as a natural reactor, then the galaxy might be full of habitable worlds that never crossed that first, critical threshold. From this perspective, we may not be late to the party, we may be the only guests who ever arrived. Needless to say, as compelling as the nuclear geyser hypothesis may be, it's not without its critics, and there are valid questions worth exploring before declaring it the cradle of all life. Some critics raise what's known as the sodium problem, the idea that life couldn't have originated in salt-rich environments, since modern cells rely on potassium and actively exclude sodium. But this assumes life's earliest ancestors shared the same chemistry as modern cells. That's a shaky assumption. Early protocells may have been far more flexible, relying on RNA and looser membranes. They might have tolerated sodium-rich environments just fine, especially if those settings were rich in energy, phosphorus, and catalytic metals, like the mineral-laden zones around a uranium geyser. It is worth noting that we still don't know how salty early oceans were, or even how and when they fully formed. So while sodium is a concern, it's likely not a deal-breaker. Plus, we have some reason to believe these geysers might even have been sodium poor themselves, potentially removing the entire problem. Additionally, phosphorus presents the opposite problem. It's often too scarce, not too abundant. Phosphorus is essential for DNA, RNA, ATP, and cell membranes, yet it's not always readily available in prebiotic settings. As we said earlier, a natural nuclear reactor may offer a solution. The process known as neutron transmutation doping, well understood in semiconductor science, can convert silicon-30 into phosphorus-31 via neutron capture, followed by beta decay. Since silicon is abundant in Earth's crust, and natural reactors emit copious neutrons, this may have been a subtle but vital mechanism for enriching early environments with phosphorus. I tend to be a bit dubious about nuclear transmutation producing this in sufficient quantity, but if nothing else, it would add some, and any helps an abiogenesis candidate site's odds. Another question is whether a geyser is truly necessary. Certainly, geyser-like systems offer advantages. They cycle fluids, trap gases, regulate temperature, and help distribute early life forms once they emerge. But similar cyclical behavior can occur deep underground. If a natural nuclear reactor forms below the water table, the same thermal pulses, heat, boiling, and cooling, can create self-regulating chemistry even without surface venting. Organic molecules may still concentrate and polymerize in these subsurface settings, and life could spread slowly outward through seeping groundwater, tectonic fissures, or eventually meteor impacts. Finally, we should note that the nuclear geyser hypothesis is not meant to rule out other possibilities. There are many models of abiogenesis: hydrothermal vents, clay surfaces, volcanic springs, ice matrices, and all have merits. What sets the nuclear reactor idea apart is the combination of features: heat, radiation, free electrons, rare catalytic minerals, pressure, confinement, and cyclic behavior. These are not individually unique, but together they may create a nearly perfect storm for prebiotic chemistry. I should also note these could overlap too. Odds of one of these candidates being on or overlapped with a natural fission reactor are likely a lot better than random placement. Regardless, it's not the only path life might take, but it may be one of the best. Fictional Exploration. You can be forgiven if you haven't heard this new scientific model before. While I did mention it in passing in past episodes, we don't normally hear of new theories until they are popularized in fiction. That will be happening for the nuclear geyser theory sooner than you think. P.A. Kramer, my collaborator on this episode, will be releasing his hard science fiction novel, Modus, the day before this episode airs. As we dug into the details, I decided the hypothesis deserved an episode of its own, and he was kind enough to share notes, research, and editorial feedback through the writing process. In his novel Modus, humanity doesn't find life in the warm shallows of a Martian pond, but deep underground, 5 kilometers beneath the surface, near a rich deposit of uranium ore. The subterranean city above depends on that uranium for survival, and the discovery of alien life, rooted in the same radioactive elements that power their reactors, becomes the catalyst for a desperate mission to save a lost colony. It's a poignant reflection of the idea explored in this episode that nuclear fire may be both creator and destroyer, a force capable of igniting biology or extinguishing civilizations. Modus grounds this concept in hard science fiction, exploring not just the implications of deep life, but the challenges of living in a closed, resource-limited system beneath a barren world. The name Modus comes from in-modus resource utilization, instead of in-situ resource utilization, due to the colony's need to stay in motion, tunneling through the rock in search of resources. It's exactly the kind of imaginative leap we need. Science thrives when fueled by creativity, and science fiction helps us envision the strange and wonderful outcomes of ideas like these, not just as thought experiments, but as living, breathing worlds. Among his many works, Enrico Fermi gave us 2 powerful legacies: the world's first man-made nuclear reactor and a haunting question about our cosmic solitude. It is more than a little poetic to imagine that both might be connected, that the silence we hear in the stars could be answered by the very element Fermi helped unleash. If life on Earth truly began in the radioactive heat of a natural reactor, then uranium wasn't just a source of power or a weapon, it was a spark, a fleeting gift from ancient stars, burning just long enough to light the fire of biology. And perhaps it was a gift given only once, or only rarely. That would make life not inevitable, but precious, not common, but miraculous. And in that view, perhaps we are not just alone because others failed, but because we are the only ones who ever passed the first great test, starting out. If you enjoyed today's episode, please like, subscribe, and share it with others who enjoy deep dives into science and futurism. A special thanks to P.A. Kramer for joining us in this collaboration. Be sure to check out his novel Modus, available now. And for more on science behind nuclear energy, early life, and the Fermi paradox, you can find a companion article on his website, pakramer.com. Until next time, thanks for watching, and have a great week.